Hi everyone, I'm Nitin Jadhav. I'm a senior software engineer at Microsoft and I work for the Azure Database for PostgreSQL team. The talk you're going to watch is about PG DuckDB in action, accelerating analytics on Azure Database for PostgreSQL. If you have ever wished your Postgres database could just answer an analytical query faster without you first exporting data somewhere else, then this talk is for you. By the end of this talk, you'll know exactly how PG DuckDB makes that possible and you'll see it running live on Azure Database for PostgreSQL Flexible Server. Okay, now let's jump into PG.DB in action, accelerating analytics on Azure Database for PostgreSQL. Here's what I'll cover today. I'll start with what PG.DB is in just few words. Then I'll spend few minutes on the strengths of Postgres because we are not here to replace Postgres. And then the limitations for analytics, which is the gap PG.DB fills. I'll then introduce DuckDB and then compare these two Postgres and DuckDB engines side by side. Then go under the hood how Postgres processes a query. And then let's understand how PGDuckDB plugs into that pipeline. After that, I'll explain the things PGDuckDB lets you do with the help of demo on Azure Database for PostgreSQL. And then finally, key takeaways to walk away with. I'll start with what PGDuckDB is. PGDuckDB is a Postgres extension that brings DuckDB's analytical engine inside your Postgres database. So you don't have to change databases, you don't have to sync data anywhere. You just enable an extension and the same Postgres server now run analytical queries with a columnar vectorized engine. And you can still be on the same reliable Postgres for your transactional workload. It's like bringing the capabilities of OLTP and OLAP at one place. To explain why this matters, let's first spend few minutes on what Postgres is great at. Postgres is the world's most trusted open source relational database and it has earned that reputation. It's a ACID compliant, so you don't lose data, you don't see half written transactions. It has rich extensibility, custom types, custom operators, and an extension model that lets us build things like PGDuckDB. And it has a vibrant open source ecosystem. There are lots of contributors, decades of hardening, and this is the foundation. On top of that, Postgres is a battle tested for OLTP, high concurrency, lots of users, lots of small transactions per second. It has a rich set of indexes like B-tree, GIN, print for very different access patterns. And it runs mission critical applications worldwide, from banks to airlines to your favorite SaaS applications. But it struggles with one specific thing, that is analytics. And it does so for very good design reasons. Let's discuss about this later. Before that, let's first understand a bit about what is OLTP and OLAP. OLTP, it's a online transaction processing, is what Postgres was born for. Lots of insert, update, delete. Each query touches a few rows. Here we optimize for low latency per query and the data stored in a row-oriented fashion. And if you want, and here we want high concurrency because thousands of users hit this database at the same time. And then we have OLAP, online analytical processing, is the opposite. For queries, few queries here, but each query is a huge. Big select with aggregates like sum, average, count. Here we optimize for a throughput, and the data is stored in columnar storage because we usually need few columns out of many, and a single query may scan millions or billions of rows. So I can say that OLTP is like a million single row queries, whereas OLAP is a single query over million rows. Same data but different physics. So when we ask Postgres to do the second job, what actually goes wrong? Three things. One of them, none of them are bugs here. All of them are design choices that are right for OLTP but wrong for OLAP. So the first one is no columnar storage. Postgres reads entire rows even if query needs only few columns out of many rows. So sorry, out of many columns. That's a wasted eye on every analytical scan. And there's no vectorized execution. It processes data one row at a time, which means CPU caches and SIMD instructions are largely unused. And there's a limited parallelism. Yes, parallel query exists in Postgres, but it's nowhere near what purpose-built OLAP engines do. None of these are actually showstoppers for your bank balance lookup, but they are showstoppers for an aggregation over billion rows. Let me show you what row IO waste looks like. So here you can think of we are running select sum of revenue from orders at the both side. On the left we have row based storage, which is Postgres. To compute the sum, the engine has to read every row and all four columns, even though we only care about the revenue column. So that's three columns of pointless IO on every page, every block, and every disk seek. And on the right side, we have columnar storage for DuckDB. Each column lives in its own contiguous chunk. So the engine reads only revenue column in the compressed batches. So that's why we gain a huge performance here. So this brings us to the DuckDB itself. So the DuckDB is in process analytical SQL database. Think of it as an SQLite of analytics. It's a small, embeddable, zero config, and ridiculously fast at analytical queries. And it's an open source, and it just in just few years it's become the default choice for in process OLAP. Now let's see why. Four things that make DuckDB special. The first one is it's in process. There's no DuckDB server. It runs in an inbuilt sorry, it runs as a library inside your application. There's no daemon to deploy, there's no port to open, there's no cluster to size. Second, the columnar plus vectorized execution. The data is stored in columns and processed in batches of thousands of values at a time. And third is automatic parallelism. DuckDB looks at your query and it tries to use every CPU core it can. And the fourth is this one matters a lot for our story, native data lake support. DuckDB can read, write Parquet files, CSV files, JSON, and Iceberg files directly, whether you are on local disk or on Azure Blob Storage. Now let's put two engines side by side. Here both are same model, that is relational model, but few different design choices. The first one is workload. Postgres is for OLTP transactions and DuckDB is for OLAP analytics. Storage. Postgres is row oriented, whereas DuckDB is columnar storage. Execution model. Postgres uses the classic Volcano iterator, one row at a time. DuckDB processes vectorized batches. Concurrency. Postgres is built for many simultaneous users with MVCC. DuckDB is optimized for one big query at a time. Neither is better here, they're all solving different problems. Then we have parallelism. Postgres has a parallel query, but it's bounded, whereas DuckDB parallelizes across all CPU cores. Data sources. Postgres reads tables stored in Postgres, but DuckDB also reads Parquet, CSV, JSON, Iceberg files in the object storage like Azure Blob Storage without loading them. Architecture. Postgres is a classic client server database, whereas DuckDB is a in process embedded inside whatever calls it. And that is exactly what PGDuckDB does. So this brings us to a headline slide. So here's the equation. On the left, we have Postgres, which is ACID, MVCC, matured ecosystem, OLTP champion, and the one weakness is analytics. On the right, we have DuckDB, which is columnar, vectorized, lightning fast for OLAP, native Parquet and Iceberg support, and one weakness is no transactions, no concurrent OLTP. Plus those two engines, you'll get PGDuckDB, and you keep the strengths of both OLTP in OLTP and OLAP in one engine. Acid safety preserved, DuckDB speed for analytics, read Parquet, Iceberg, or blob storage from plain SQL, and critically, no new system to learn or operate. It's still the same Postgres your applications connect to. So how does it actually do? Let's look at Postgres query pipeline first. It's a quick refresher even if you have seen this 100 times. Postgres takes a query, and then the parser tokenizes the SQL, builds a parse tree, validates the syntax, resolves table and column names, and then planner is a cost based optimizer. It looks at statistics, decides join order, picks the indexes versus sequential joins, and it gives the plan. And then executor takes that plan and runs it using volcano model. It pulls one row at a time through a tree of operators. That row by row pulling is wonderful for OLTP. Fetch the matching customer, return immediately. But for our analytical query, millions of rows passing through that iterative tree one at a time is the bottleneck. Now let's see what pgductdb does to that pipeline. So it's the same parser here, same parse tree, but the planner is hooked. When parse tree comes out of the parser, pgductdb gets a chance to look at it and ask, is this a analytical query that I can handle? If yes, then it builds a DuckDB plan instead of Postgres plan and hands it to DuckDB executor, which runs it on a vectorized execution engine and then returns rows back through Postgres to your client. So your client doesn't know anything changed. It's the same connection, same wire protocol, and same SQL. If the query isn't fit, say it's an insert or it touches features that DuckDB doesn't support, pgductdb quietly hands it back to the Postgres planner, and that's a automatic fallback. You never break, and you just sometimes get faster response. So now let's understand what exactly triggers this hook to actually take over. So there are three triggers. The first one is you set duckdb.force execution to on. From that point on, every eligible select queries are routed to duckdb. So it first checks whether this can be executed on the DuckDB. So if it is feasible, then it runs on the DuckDB. Otherwise, it falls back to Postgres. And the second, the query reads data lake files like anything calling read Parquet, read CSV, or read JSON. Such things DuckDB owns those automatically. And third is if for any reason DuckDB can't handle a query, then it falls back to the Postgres transparently, as I already explained. There's no errors and there's no broken applications. So what does this let you actually do? So there are three superpowers and all of them are available on Azure Database for PostgreSQL. First one, accelerate your existing Postgres tables. So you set duckdb.execution to on, you run the same group by you have always run, and the duckdb executes it. Same table, same SQL, but a faster response. Second one, you can read and write blobs directly. There's no copy, there's no ETL, there's no extra service to manage. And the third one, and this is my favorite, that is hybrid analytics. So you can join a live Postgres table, say your customers table with the Parquet files in the blob. Say it's a 3 years of historical orders in the same SQL query. So you can join this live operational data plus the historical archive in one engine in the engine you already use. So that's very powerful. All right, let's. That's enough of slides. Let's see the demo. So here's exactly what you're about to watch in next few minutes. So there are five things end to end. First, I'll provision a brand new Azure database for PostgreSQL flexible server. And second, I'll install the pg.db extension on the fresh server created. And then I'll run a tpch queries with a Postgres engine, then run the same queries with a DuckDB engine, and then we can compare. Fourth, I'll read and write Parquet files directly from the Azure Blob Storage. And fifth, hybrid analytics. I'll join a Postgres table with a blob in a single query. So three things to watch here. The query time difference between two engines. So whenever I run a query on DuckDB execution engine and Postgres engine, so you can please watch out like the differences. the plan switch when exactly we the duckdb dot force execution kicks in, and the fact that actual SQL itself doesn't change, only the engine changes. Okay, so now I'll start the demo. I will demonstrate how we can accelerate analytics on Azure Database for PostgreSQL flexible server using PG-DuckDB extension. First, I'll create a new flexible server instance. I'll name the server as PG-DuckDB demo. I will now enter the required configuration details such as server version and the administrator credentials. Once the configuration is complete, we can go ahead and create the server. This usually takes some time while the platform allocates and initializes the service. The server provisioning is now complete and our flexible server instance is up and running. Next, in order to use PGDuckDB extension on flexible server, we need to enable it at the server level. So first, I'll update the server configuration by adding PGDuckDB to the Azure.extensions parameter. Then we also need to include PGDuckDB in the shared preload libraries parameter. Let's save and restart the server so that the new settings take effect. The restart takes a moment while the server shuts down gracefully and starts again with the updated configuration parameters. The restart is now complete and the server is back online. At this point, PGDuckDB is available and ready to use. Now let's connect to the server using PSQL. Once connected, we simply enable the extension in our database with a create extension query. The extension has now been successfully created. The installed PGDuckDB extension version is 1.1.0 and it internally uses DuckDB version 1.4.3 as its analytics engine. In this demo, I'll show two use cases of PGDuckDB extension. The first is accelerating analytical queries by using DuckDB's vectorized execution engine on data stored in flexible server. For the first scenario, I have already loaded TPCH benchmark data with scale factor 5. That includes about 5 GB of data in line item table, around 1 GB of data in orders table, and about 145 MB of data in customers table. Let's now run a few TPCH queries and compare the performance. By default, duckdb.force execution is set to off, which means the query runs using Postgres execution. First, we will run the query using standard Postgres execution engine. Let's start with TPCH query 1. This query performs aggregations over the line item table and scans a significant amount of data, which makes it a good candidate to observe analytical execution performance. While the query is running, Postgres is scanning the rows and computing the required aggregates using its traditional execution model. With Postgres execution, the query completes in about 26.6 seconds. Now let's enable DuckDB execution by setting duckdb.force execution to on, which forces the query to run using DuckDB execution engine. Running the same query again, you can see it completes in 11.1 seconds, which is 2.4 times faster. That's a nice performance improvement, and importantly, we achieved it without changing the SQL query. Now let's switch to Postgres execution and run TPCH query 13. This run completes in 7.7 seconds. Now we run the same query with the DuckDB execution enabled. This time, the query finishes in about 4.1 seconds, which is close to 2 times faster. Again, it's a very nice improvement for this analytical workload. Now let's see another example. First, let's switch to Postgres execution. Next, I'll show the query that demonstrates a classical analytical pattern, multiple count aggregations per group. In this query, we filter orders between 1993 and 1996 and then group the results by order priority. For each priority, we compute the number of distinct customer, number of distinct clerks, and number of distinct orders. Queries like this are relatively expensive in traditional row-based execution. With Postgres execution, this query takes 15.7 seconds on this dataset. Now let's run the same query using PGDuckDB execution. Here DuckDB processes the data in vectorized batches, which allows it to apply vectorized aggregations very efficiently. This time, query finishes in 2.3 seconds, which is nearly 7 times faster. That's a significant performance gain without changing SQL and without moving the data out of Postgres. Now let's move to the second part of the demo, where I'll show how to read and write Parquet files stored on Azure Blob storage directly from flexible server using PGDuckDB extension. To allow DuckDB to access files in blob storage, we first create an Azure storage secret. In this step, we register our Azure storage credentials using the create Azure secret function. Once this secret is created, PGDuckDB can securely access files stored in our blob containers. For this demo, I'm using a historical stock trading dataset stored as Parquet files in the blob storage. Let's first quickly read the dataset using read Parquet function. This simply verifies that the Parquet file is accessible and gives us the preview of the data. Now let's run a slightly more interesting query. Here we query the same Parquet file directly from the blob storage and retrieve the 10 trading entries with the largest price movements. What's important to notice here is that the data remains in the blob storage, flexible server does not ingest or load this dataset, and DuckDB scans the Parquet file directly and returns the analytical results. The next part of the demo demonstrates hybrid analytics, where we combine transactional data stored in Postgres and analytical data stored in Azure Blob as Parquet file. Let's start by creating a small Postgres table to represent a portfolio watch list. Let's insert a record for a stock we are monitoring. This table represents operational or transactional data that typically lives in Postgres. Now for the interesting part, we take the watch list table stored inside Postgres and the latest closing price from our Parquet dataset in the blob storage and join them in a single query. That's a result. So we are effectively combining operational database data with external analytical data stored in blob storage all through a single SQL statement. No ETL pipelines, no intermediate ingestion step, and no data duplication. That's a really powerful capability for hybrid analytical workloads. Finally, let's write result back to the Azure blob storage as a Parquet file. And here we see that the file has been created. And let's also see that the content of the file by reading it using read Parquet function. And here is the data we have written. That's awesome. Postgres can read external Parquet data, analyze it, combine it with external tables, and then write the results back to the Azure blob storage. We can seamlessly analyze large data sets stored in Azure blob storage, combine them with transactional data in Postgres, and produce analytical outputs all using standard SQL. That's a powerful analytics with PGDuckDB on Azure Database for PostgreSQL Flexible Server. And this capability is now available on Flexible Server versions 14 through 18. I encourage you to explore it and see how it can simplify analytical workloads and accelerate analytical queries on Flexible Server. Thank you. I hope you all enjoyed the demo. Now let's wrap with key takeaways. Four things to note here. One, uh, the uh, the first is it's only one database, two engines. So Postgres is for OLTP and DuckDB is for OLAP in the same managed server. Second is no data movement. You can query Parquet on Azure Bob directly from SQL. The data lake doesn't have to come to the database, and the database doesn't have to come to the lake. And the third one is hybrid analytics in one SQL. So you can club live Postgres tables with the data stored in the blob storage in a single query, and same SQL faster answers. You just set duckdb.force execution to true, and your existing queries don't change. Yeah, that's all from my side. Thank you.